Hello, this will be the last video of this first theoretical section, and in the next section you will get plenty of examples. And well, if you want to, you can keep this last theoretical video until the end of this course and watch it after you have seen several examples of proofs by induction. But well, I present this video now because I find that it belongs to this first theoretical part. Let's start. Both cases are necessary. And what does it mean? Well, you have seen that in each induction proof you have a base case and you have the induction step. And now I will show you two examples of theorems which are obviously false. You will see at once that they are false. And in each of them, only one of these two will work, which will show that, well, you really need both the base case and the induction step. So what is the first example? The first example shows that the base case is essential. Because without a base case, I can prove such a nonsensical theorem that all the natural numbers are equal to each other. Well, it's obviously not true, right? But if you write this in this way, that each natural number is equal to the next natural number, then you will kind of say that all the natural numbers are equal to each other, right? And it happens that you can actually make an induction step out of this. Because how would t of n plus 1 look? Well, t of n plus 1 would look that n plus 1 is equal to n plus 1 plus 1, it is n plus 2, right? So this would be t of n plus 1. And obviously, if you assume that t of n is true, then t of n plus 1 will follow, because you know you are allowed to add the same number to both sides of a true equality, right? So if you assume that this one is true, then it will remain true if you add 1 to both sides. And this will exactly be the induction, the thesis for this n plus 1, for the next one, right? So the induction step works. But the problem is that you have no starting point, because, well, 0 is different from 1. So the induction step shows that if some number is equal to its successor, the next number, then the next natural number is equal to its successor. So the induction step works, but the problem is that we never start with a true statement, because the statement, the base case, would be 0 is equal to 1, and you know that it's not true. So this example shows that the base case is essential. You need to have one statement in the beginning what is true, so that you in combination with the induction step get a true theorem. And the second one will show why the induction step is essential. So here you can guess that the base case will be true, but then the induction step will not work. And what is the nonsensical theorem which are going to kind of prove? That each natural number is equal to its own square. Well, you know that it's not true, right? 2 and 4 are not the same number. But okay, let's pretend that we want to prove this one. So let's see how our t of n would look. Well, that each number is equal to its square, right? And then t of n plus 1 would look like this, that n plus 1 is equal to n plus 1 all squared. And let's see the base case. This one is true, right? Because 0 is equal to 0 squared. Even the next one, 1 is equal to 1 squared. This is still true. But of course you know that it's not true for the next one. But okay, let's say that we have proven the base case. The base case is true. But now, what is happening with the induction step? So in the induction step, we want to know if we can conclude the truthfulness of the statement for n plus 1 if we assume that t of n is true. So, in other words, if we assume that for some n, which is greater than or equal to 1, n is equal to n squared, can we can we conclude from this that n plus 1 is equal to n plus 1 squared? So you see, we have to use this assumption in some way in order to prove this. Okay, we can start in some way. We can write this as the square of a sum, which is n squared plus 2n plus 1, right? And the question is if we can conclude that n plus 1 is equal to n squared plus 2n plus 1, assuming that this statement is true. So let's say that this statement is true. Then n is equal to n squared by the induction assumption here, and of course 1 is equal to 1. But you see the problem, right? Here at the left-hand side of this statement, which should be true, provided this one is true, you have n plus 1, and here you have n squared plus 1, which is equal to n plus 1 by assumption. But you still have one guy which is disturbing the situation, because, well, if n is greater than or equal to 1, then you have a problem. This is not 0, right? So you will not have this implication. So in this second case, the induction step doesn't work, because provided this, we don't get that this is equal to this, because this guy is destroying everything. And it's good also because this is simply a false theorem. So here we do start with a true statement, but the transfer between the numbers doesn't work. So the fact that t of n is true doesn't imply at all that the statement is true for the next number as well. So now you have seen that both base case and the induction step are very important, are essential. Without them we don't have a proof. And you also know that this induction step is the harder part, the part you have to work with. The base case is easy, generally. Thank you for watching. Bye-bye.